Okay, we're going back to this discussion, exploration 1 on page 298. Trying to finish that up. There'll be a little bit of redundancy here at first. We get everybody back on track. Remember what we were doing? We contrived that crazy integral. We said it has to go through the 0.35, so we just made it go through and it's all that cheating. Remember that?
That's what I liked it.
Yeah. Well, we're taking that very curve and trying to graph it, and then what they ask you to do is to start by graphing it on the standard screen from -10 to 10, -10 to 10. I need you to understand what the calculator is trying to do. It's trying to find the area between the curve, the tangent, between the tangent curve and the x-axis. Very first thing it wants to do is this, because that's the very first x in that window. And so it's trying to find the area under the curve from 3 to -10, and it's having to cross several asymptotes that it can't fill in the gaps on, and that's why you got an error. That's what it's trying to do. If it could do that, then it would go to maybe -9.993 or something. They can't do that either. And so the reason why the calculator got hung is because it had to cross some asymptotes in trying to fill out the area, and that can't be done. Infinite discontinuities cannot be fixed. So if I put an x here, it's got to be such that the point where the 0.35 that we made it go through is going to be in the branch of the tangent curve that has the point x equals 3 in it, which is about right there, because pi is 3.14. So it's about right there, and so this is the branch we're going to talk about. And so we want to integrate from, well, we want to find from, we want to restrict the window to go from -pi/2 to 3pi/2, but just slightly to the right of those, so we don't actually include the asymptotes. Do you remember that? Yes or no?
Yes.
Yes? Okay, then fix your window again if you've been messing around and doing homework. Heaven forbid.
Silly.
Go to x min of pi/2 plus 0.001. And let it max out at 3pi/2 minus 0.001, we decided. I'm going to scale it by pi/2. And I'll let the y's go from -10 to 10. I'll leave that alone. Okay, now if we've got that window, what is it we want to graph? Do we want to graph the tangent x, or do we want to graph that integral? Okay, let's graph the integral. So you go to y equals, if you've still got that in there, that's great. I don't, I had to do other things with my calculator yesterday. So I would put in math 9 to get my integral. I go 3 to x, tangent x. Make sure you're in radian mode. I'm sure you probably haven't left radian mode, but I do that all the time. With respect to x, plus 5. After the dx, put plus 5. And then graph that. And it may take it a minute or two, but if you've restricted your window, it will graph because it has no longer running across asymptotes.
You can just watch your battery power.
It comes in really slow because an integral, even for a CPU, is tough.
Nice.
Riker, did you put it in and are just waiting?
No, I didn't take it out from yesterday.
Is that a strange looking graph to you? Does that feel funny to you? It's because what you're seeing is actual values of area at certain x's. That's what you're looking at. Values of area. So it means that it's calculating this little teensy weensy bit till it gets to pi, and then wherever x is, and if we put x, we let x go clear to the edge of the, well, it's going from 3 because that's where it starts over to an x that's really, really close to this. So what you're seeing is graphs of these areas at every x, and it's accumulating. You know what I mean? Out to very close to the edge of the screen there. And so it keeps adding more and more and more and more, and you keep getting more and more and more and more area. The reason why it dips down like that right towards the middle is because of the belly in this curve right here. It doesn't add as much right in there because it leans this way, but then it starts adding more and more and more. I don't know. You don't have to understand all that. Don't worry about it. But this is the graph of areas from 3 to there. And the reason why it's above the x-axis a long ways is because of this. It's got a minimum of 5. Even if this were 0, that would be 5. I mean, that's why it's up above, adding 5. Okay, so sometimes you gotta be careful if you're trying to integrate with your calculator, you just can't do it blindly.
Sorry, I was in a meeting in the counseling office.
Okay, I'm sorry you're gonna miss this. You were in the counseling office?
Yes.
You gonna be here for a while?
What?
I thought you said you were going to be in.
No, that's where I was just earlier.
Okay, all right.
It's gotta regret.
All right, we just kind of finished up exploration 1 with that tangent thing, and the reason why you gotta set your window to just inside the asymptote so that it doesn't have to try to do that. Okay, so now I want to talk to you about the fundamental theorem part 2. We've actually already discussed this. So I'm going to erase this up here, and we're going to start talking about that second half, the one where you actually get to calculate things, because Riker was so excited about that. He didn't like the theory. He wanted to be able to calculate, or maybe it was Kyle.
It was totally Kyle.
It was totally Kyle. Because Riker is a mathematherist, right?
Yeah.
Okay, all right. Okay, this, if you'll remember, was the second part that we discussed, which is if you want to find the integral from A to B, you want to find an actual number of a function, then this is the part that a lot of you missed on your quiz. Then you have to find the antiderivative of f, which we call capital F, evaluate it at B, and subtract the antiderivative at A. Some of you just use that function. You have to antiderive before you plug it in.
We also have to do the 1 over B minus A.
That was if you were doing an average value. This is just the area under the curve. This is the second part. This is the second part of the fundamental theorem. This is the part that engineers use to actually find numbers to calculate with. The other was theory. Okay? So that's what we're talking about now. And they show you that on page 299. They use capital S and little f's and A's and B's and everything. It's all right there. They do a proof for you, and his proof is really clunky. I proved it for you. Much more elegant. It's on the paper that's handwritten in my hand. There you go. So on example 5, we're going to apply this by actually muscling through it without using the calculator. You can almost check it with your calculator, but if it says show this out or show it analytically, you're expected to show your work for full credit. So this is one we can do. It's just a polynomial. It's the integral from -1 to 3 of x cubed plus 1. If you wish to find the area under the curve, x cubed plus 1, on the interval from x equals 1 to 3, this way, and you're doing it analytically, what's the first thing you got to do? You got to antiderive the function, and we're going to call it capital F. What is capital F in this case?
1/4 x to the 4th plus x.
1/4 x to the 4th plus x. Now, I need to know if anybody's having trouble understanding that part. It's okay if you are, because this is new. I'll understand the antiderivative. Boston's on top of it. Okay. Is everybody clear with F? Now, to actually find the area under the curve, I need to find F of what? 3 minus F of negative, or sorry, F of 1.
I think it's negative 1.
Is it -1 here? Sorry. Okay, sorry about that. So now that we have capital F by antideriving, what is F of 3?
28.
23.25.
2.5? Oh, yeah. It's 81/4 plus 3. And 81/4 is 20.25, isn't it? 80/4 would be 20.
Yeah, that's what I got.
So 81, I know that's what you got. I'm trying to teach you the arithmetic. 81/4 is like 80/4, which is 20, plus another fourth, which is 20.25. Then you got to add that 3 again. That's where the 23 comes from. Y'all see it? So that would be the arithmetic if you didn't use the calculator at all. Now, what is this one?
0.25, -0.75.
This is, right, it's negative 0.75, because this to the fourth, negative 1 to the fourth is just 1, so I have 1/4 minus 1. That's negative 0.75,
But you have to subtract it. So
which
you
makes
just get 24.
this plus, and you get 24. Nice.
I like it.
Okay, so that wasn't too bad, right? You can do the arithmetic when you do this on your calculator, but I want to see the antiderivative analytically done, not just plunk that in your calculator. You can check it that way. You check the integral now and see if that's what you get. Okay, did you anybody check it with the integral? Boston's on it, man.
Yeah.
Yeah, it's 24. Okay, now, I'm going to erase this. It's in your book. It should be in your head. Get it in your head. You always do the top one, f of the top one minus the bottom one. So get it the correct order. Now, I want to take a look at this a little bit more. No, not that one. Sorry. I'm doing that one. If I have a function y equals 4 minus x squared, and I'm going to look at it on the interval from 0 to 3. Do you have an idea in your mind what this thing looks like? Anyone?
Yeah.
What is it?
Upside down parabola.
An upside down parabola with a vertex at 4 on the y-axis. And a regular opening one that's not fat or skinny, right? I want to look at that graph for just a minute. And I want to look at that graph only on the interval from 0 to 3. So up here at 4 is where that thing comes down. And I don't want to look at this half over here. I want to look at this piece over here. It's going to come down like this. And if you'll remember how to count this out, we would go out 1, down 1, out 1, down 3. Do you agree? So this is 2. This was 1 when x is 1. This is when x is 2. And I've got to go clear out to 3. So 3 out here is going to come down here somewhere. And that would be, if we did it again, out 1, down 5. So I got to split this up. That looks really gross, but come down there. So this would be negative 5, right? Okay. When it says to find, just pretend that's nice and smooth, okay? When it says to find the integral or the area under the curve of this curve from 0 to 3, it means this integral from 0 to 3 of 4 minus x squared dx. That would be the integral. And that number that you get out of that would account for this space minus this space. That's what it would do. If I wanted to find the actual space that I have to paint from 0 to 3, that would have to be positive, and so would this. Wouldn't it? So then, if I wanted to find the area, we need to do the integral from 0 to 2. And add on, well, would I be adding on? Yeah, I want to add on that area, but that area is negative. So if I subtract a negative, I will be adding it on. The integral from 2 to 3 of that same thing. You see why this is negative?
Yes.
Because this is negative, and I want to add them together to get total paintable space. Okay, so what is the antiderivative of this?
4x minus 1/3 x.
4x minus 1/3 x? And I've got the same thing over there. So it's this that I want to evaluate, first of all, from 0 to 2.
It's 1/3 x cubed.
Oh, thank you. Thank you, thank you, thank you. And I'm going to evaluate that from 0 to 2. And then I'm going to subtract that same thing, 4x minus 1/3 x cubed, from 2 to 3. And that will give me total paintable space because that negative, I know that feels counterintuitive, but we're subtracting a negative here. Okay, so what do I get when I put a 2 in here?
8 minus 8 thirds.
8 minus 8 thirds, which is 24 thirds minus 8 thirds, and that's 16 thirds. And subtract, I've got an x in both of these, so when I plug 0 in, I get nothing.
0.
Okay? minus, now over here, I'm gonna plug a 2 in, but I already did that. That's 16/3. No, that's what I'm gonna be subtracting. I gotta find f of 3 now, and that's gonna be
12 minus 9.
12,
30.
12 minus 9, yep, 3.
So 3.
Does that make sense? 12 minus 9? This is gonna be 3 plugged in here. 4 times 3 is 12. 3 cubed is 27, divided by 3 is 9. Yep, 3. So I get 12 minus 9, which is 3 minus 16/3. That's 9. Okay, let's go ahead and do the arithmetic. That's gonna be 16/3 minus, this is 9/3 minus 16/3, which is 7/3 negative, but it's negative, negative. So I get 23/3. Thank you. Okay, but you know how we love mixed numbers. I hate them, so that, well, whatever.
I shower now after seeing that.
What happens if you, folks, what happens if you just do the integral here? What if you just evaluate the integral? What do we get for that?
Oh, you do the 3 1 minus 3 1, so it's 3 minus, it's 3.
It's gonna be this minus this, right? Which would be 9/3, which is 3. So the integral, which accounts for positive and negative space, is 3. But if we add up that space instead of subtract it out, we end up with a little more than 7. Well, almost 8. You following me there? It was all based on knowing this point that intersect on the y-axis, on the x-axis. So you can see sometimes knowing that intersect serves lots of purposes. But we knew what that was by counting out the parabola. It hit right there. It was a 2. If it's not a 2, then your integral maybe go from 2 or from 0 to 2.738 and then 2.738 to 3 or something like that. However, big however here. Wouldn't it be nice if we could take this area, whatever it is, and put it up here?
Why would that be nice?
Because it'd all be positive and I could just integrate from 0 to 3, period.
That's the absolute value. Yeah.
Like, well, it's not that hard to just add them.
That's absolute value.
So if you absolute value 4 minus x squared, would it give you that graph right there?
And then keep
Yep.
going.
Whoa, I'm gonna do that in code. That's weird.
I didn't really
Okay.
enjoy that.
Yeah, why don't you do that? Graph the absolute value of 4 minus x squared and let your window only go from 0 to 3.
It makes me uncomfortable.
What the? That's kind of weird. I'm not.
Did it work? Did it look kind of like mine?
Yeah.
Yeah, kind of like went boing.
Yeah. Kind of went boing on mine too. It came down with boing. Yeah. Does it look kind of like this black stuff up here? Kind of?
Oh,
Yeah.
especially when I do the same window. Now it really looks like it.
Yeah, I told you. 0 to 3. Let this go up to 4 or a little higher. Maybe go from 0 to maybe 4.2 or something. It should look like this.
So is that your shortcut way to do it? Is you use the absolute?
It's not a shortcut. It's very, very conceptually oriented. So here's the deal. This would give you the integral, which accounts for positive and negative area. This would give you the area directly without this stuff if you did this.
How do you think that arrived?
Now, if you're going to try this by hand analytically, it's not going to work. I haven't taught you how. I'm not going to spend the time to teach you how. Okay? The way you do this analytically is to do this. The way you do this in your calculator is to stick an absolute value on it before you integrate. Well, as you're integrating. Now, people get this mixed up, folks. This right here is not the same as this. You don't absolute value the integral. You absolute value the function you're integrating. So don't get absolute value happy. Put the absolute value after you've told it to integrate. This is not the same.
But since that area is always positive, if you absolute value the absolute value equation with that, actually not that bad.
No, what you would do is absolute value this, which would give you 3.
Yeah.
Yeah, right, yeah. So they're not the same. And if this integral had more negative space than positive, and this was -3, putting that absolute value in the integral would just change that to a positive. Doesn't do what you want to do. Absolute value of the function.
There's no application of this, but if you do the absolute value of the equation rate and the absolute value of all things, that probably still works.
Absolute valuing this gives you positive area.
Yeah.
Absolute valuing that, which is absolute value that positive number. It'll be redundant. Okay, folks, listen. I want you to look at the graphs and just a little more revisiting of this concept. Just listen. On page 301, on the left side column, you see those two green graphs. And if you were to integrate that first one, what would you get?
0.
0. If you were to integrate the second one, you would get positive or negative? Positive. And can you see that going from the first one to the second one just took all the negative spaces and tipped them up?
Yep.
That's absolute value.
So that's good for finding when you want the whole area.
The paintable space. That's how I refer to it. You're going to cover it with something that's got to all be positive, whether it's above or below the x-axis. Sometimes the integral is appropriate, sometimes the absolute value is appropriate. That's up to you to decide. But now you know. Now you can find the integral from 0 to 3 and find paintable space without splitting it up into positive and negative spaces. You can just absolute value. But you have to use your calculator to do it. Okay. Lest you get too excited about always using your calculator, I want you to look at example 8. These kinds of problems are wonderful for testing. It tests the concept. This is a little bit hard at first. Please don't blurt out any answers unless I call on you. Kyle. Landon.
No, I don't yell answers unless they're wrong.
Boston.
I always yell answers. Always.
Okay.
I'll keep quiet.
Here we go. Listen up. Take a look at that graph to the left of example 9 on page 301. Okay, it says, the graph of a continuous function f with domain 0 to 8, you can verify that for yourself there. Each one of those tick marks is 1. So it's shown in this figure. Let h, this is where it's going to get rough. Let h be the function integral from 1 to x of that function. And the integral from 1 to x means the area under the curve from 1 to wherever x is between 0 and 8. The area. So let's try to answer this. This is the first question, I'll ease you into it. What is h of 1?
0.
0. Because if you see what h is, if you put a 1 in and replace x's in the function with 1, you get the integral from 1 to 1. And I don't care what the function is, that's 0. That was easy, right? You understand we're putting the 1 in? Okay. Now look at this. Question is h of 0 positive or negative?
Is this thing right here?
See, I told you this was going to get rough in a hurry. Look at the curve and look at the space between 0 and 1. Is that area positive or negative? Positive, but we are integrating from 1 to 0, which makes all of your respective rectangles have negative widths. So even though the area is positive, the integral value is negative because you're integrating backwards. You understand what I'm saying at all?
Yes.
Yeah? The actual area is a positive area between 0 and 1, but we are integrating from 1 back to 0, which reversed our order. If we were integrating from 0 to 1, it would be positive. From 1 to 0, positive areas turn negative and negative areas turn positive. Do you understand what I'm saying? Everybody got that? So it matters which of these guys down here, it matters the lower limit. Next one. Find the value of x for which h of x has its maximum value. I've heard a lot of 4s. Everybody agree?
That makes sense.
Oh, wait, yes. Maybe yes.
Maybe yes.
Sure.
Why?
That's the most positive area.
What is h of x as a concept? It's the area between the x-axis and the y-axis, the x-axis and the curve. And there's no absolute values here, which means if we go below the x-axis, we start subtracting stuff. You see why it reaches its maximum highest value as an area at 4. Because thereafter it begins to take it away. Does that make sense? Okay, next one. Find the value of x for which h of x has its minimum. At 8, because by the time you get to 8, it has pulled off the negative area as much as possible on its way over. And by the time you get to there, is the value of h positive or negative? Negative. And it is at its farthest, the area of the integral value is at its farthest to the left by the time you get to 8, because we just keep subtracting and subtracting and subtracting as we move along towards it. You all see it? And how do you know that the value there, the value of the integral is negative? How do you know it's negative by the time you think?
Is that negative area?
Yeah, exactly, because the negative area is obviously bigger than the positive area. Yes.
So if it was super steep right there between 1 and 0, would it be possible to have more space there instead?
Yes. You could have a lot more space there, but when we talk about h, we're only considering from 1 on. So that area over there to the left of 1 is not included in these last two situations.
It's not, even though you could have 0, which is still negative area.
No, the lower limit is 1. H is defined to have a lower limit of 1.
So you can't.
You're right. We could let x go as far as 0, and that would detract from the area. So that could be considered negative area, and so is that big bubble below the x-axis on the right. So we are
The
surely,
big bubble's bigger, but.
and x could be anywhere from 0 to 8. You're right. Part E. Find the x coordinates of all points of inflection in the graph of H. This takes some thought. Find the x coordinates of all points of inflection in the graph of H.
That's what I got. It's 0. So that's the
That's true. The second derivative.
That's what you gotta get straight in your mind, is what Brent's talking about. What, with respect, listen, folks, remember what H is. Get it hard in your mind. Remember what H is? You're looking at a picture of it. See what H is? With respect to H, what are we looking at in that graph? H prime, right? And if we're asking about inflection points of H, we need to be looking at H double prime, which is this function prime, which means this function's slope. Where do the slopes of this function change from being positive to negative and vice versa? At 3 and 6.
Yeah, because 1 is
Do we consider endpoints? Like this
At 1, or excuse me, at 1, that's kind of where it starts, and I realize we could go backwards. I suppose there's an inflection point there too. We're looking for peaks and valleys of this because that's where slopes change from being positive to negative. and vice
Oh, are
versa.
we only looking on the integral from 1 to x? No, we're
Well, it does say that the whole thing is, that we need to be looking and considering everything from 0 to 8. See that interval? So that means we need to consider with that h the way it's defined by going backwards. So if we consider the whole function from 0 to 8, there is a point of inflection at 1 and at 3 and at 6. Because in every case, in the case of 1, that graph, if we look at its slopes now, I mean, we're considering the derivative of this graph, which is the second derivative of h, it goes from being negative to being positive. So we have an inflection point at 1. That's where the slopes change, right? Inflection point in h. Minimum in h prime. Are you following this or not?
Yes.
Natalia, no? Okay, shall I say it again? You wanna discuss it again? Okay. H is this function's antiderivative. So if I derive h, I'm gonna get this function. Right? If I derive this function, I will get h double prime, which is where I'm talking about inflection form. So if, what I'm looking for is where the derivative of the function I'm looking at, that blue function, where the derivative of that changes signs, is when I'm gonna have an inflection point at h. And this thing's slopes change signs at its peaks and valleys, which occur at 1, 3, and 6. You see it now?
Yeah.
That's hard. You'll get more used to it as more we talk about it, but that's a hard thing. Getting all three of those things related, where the first one's an integral. That's weird. Okay. We'll do more of that as we go along. You can see the solution on the other page, and sure enough, they have what we had, and you were right, it's from 0 to 8, and so they included 1, so it's 1, 3, and 6 on that E part. Okay? Weird and strange things to consider. Those are very conceptual. That's the reason why people who write tests love that kind of stuff. Makes sure you got it in your head how everything's related. Okay, that's all I have for you. And you can use the rest of the day to work on this.
Kyle. Where to?